Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This is the final one of 4 on motion with a variable force. I'll remind you again that with variable force you also have variable acceleration, so it's quite wrong to try to use the Suvat equations, which are based on the accelerations being constant. Let's begin with the problem. A particle of mass 0.1 kilograms is released from rest, and that's very much like the situation at the beginning of the last video. It falls under its own weight. What's different this time is that the air resistance is modelled by a force which is 0.004 v squared, and that's a model which is appropriate for high velocities, expected high velocities in the practical situation. So we'll begin with a force diagram. It looks very much like the last one, except that the resistance term has changed to 0.004 v squared. The weight is still the same form, mass times gravity, and x and v are as before. Now from that information there and the mass, we want to form an equation using Newton's second law, F equals ma. So working positive downwards, 0.1 g minus 0.004 v squared is equal to the mass times the acceleration. Now, as before, the acceleration is variable, and we're certainly going to introduce a calculus form for it. The appropriate one in this case is v dv by dx, because the question asks for v as a function of x. So my second line will simply be the same, but with the a term changed to v dv by dx. Right, now it's crazy to proceed with all those fractions. The smallest is 0.004, and that's the same as 1 over 250. So if I multiply by 250, I'll get 25g minus v squared is equal to 25v times v dv by dx. Well, that looks much easier already. Now you'll recognise there a variable separable situation, because if I were to divide by 25v, the left hand side would be involving v only and no x's. Well, in fact, what I would anticipate really is having dx by dv as, so I'm going to get 25v over 25g minus v squared. That's the most sensible way to separate the variables, in which case I'll obtain on the left that the integral of dx is equal to the integral of 25v over 25g minus v squared dv. Well, that's really not all that difficult. On the left hand side, obviously not, that's just x. On the right hand side, I'll put the constant in first, then I don't forget it. We're going to have something like log 25g minus v squared, because when you differentiate log 25g minus v squared, you'll get 1 over that same bracket, and you'll have to multiply by its derivative, which is minus 2v. Well, we haven't got minus 2v, we've got 25v, but that's nearly the same thing. If we multiply by minus 25 over 2, that will then do it. So that's our integral. Now it would be nice to go a line further. I want v equals, so I'm looking to get v squared by itself. So the obvious next thing to do would be to multiply by minus 2 over 25. That's what we'll see on the next slide. If you multiply the c by minus 2 over 25, you get another constant, which we'll just call another c, and a c dashed. So we got as far as that. Look, I called what I introduced a c dashed here, and then when I multiply it by minus 2 over 25, I've called that the new c. So the long and the short of that is that we've got an integrated equation, and we need to determine the constant. So we know that when x equals 0, v equals 0, it starts from rest. So from that we can see that 0 is equal to log 25g plus the constant. So the constant is just minus log 25g. So if we put that into the equation at the bottom, we'll have minus 2x over 25 is equal to log 25g minus v squared minus log 25g. Now, using the properties of logs, the difference of two logs is the log of the quotient. That's log 25g minus v squared over 25g. Okay, that's now set up to do something really quite powerful, which is to take exponentials of both sides. But let's create a bit more space and get up to date with a tidy version. So there we are at the foot of the page with the point I just reached. So if I take exponentials of both sides, I'll get e to the minus 2x over 25 is equal to 25g minus v squared over 25g. Then if I multiply by 25g, I'll get 25g times e to the minus 2x over 25 equals 25g minus v squared. So we're one line away from v squared equals now. So v squared on the left equals 25g minus 25g e to the minus 2x over 25. So that's 25g times 1 minus e to the minus 2x over 25. It's worth remarking that this is another terminal velocity situation, because if you let x get larger and larger, as it tends to infinity, the exponential term turns to 0, and that means that v squared is getting closer and closer to 25g. That's a typical terminal velocity situation. But the question asks us to get v in terms of x. So at this point I'll introduce the 9.8 for g, and that 25 times 9.8 is 245. So v is equal to the square root of 245 times 1 minus e to the minus 2x over 25. And that's our expression for v in terms of x. And that's the answer to the question. So here's a neater version of that. Doesn't say anything different. Let's just speculate on what else could be involved at this stage. What we did was use v dv by dx to relate the velocity to the displacement, and that's how we got, by integration, the expression that's given there. Notice that minus 2 over 25 has become minus 0.008. If we wanted to relate velocity to time instead of using dv by dx, we would have used dv by dt, as we did in the previous video. And that would give us an integral which could be calculated slightly different form, but it will be, again, standard stuff. Well, that's the end of this video presentation, and it's the end of the series of 4 on motion with variable force.